We're doing a video on the transference principle, which is a principle in real analysis, which basically tells you that you can, well, let me just read the theorem right now. So if f is continuous at x0 and an is a sequence in the domain of f which converges to the same value x0, then we know that f of an converges to f of x0, which, it sounds very intuitive. Like, let me just read this part again. So if we have a sequence and, the limit as n goes to infinity of an equals x0, then we know that the limit as n goes to infinity of f of an equals f of x0. So we just slap that f on, and basically and nothing changes. But we can only say this if f is continuous at x0, which, is kind of weird. And then again, like, what this is really saying is you can put the limit inside of a function. So the limit as n goes to infinity of f of an equals f of the limit as n goes to infinity of an. So basically we can put this limit inside of the function argument, but only if f is continuous at the limit of the sequence. And why is this the case? Well, we can easily find a counterexample right now. So let's imagine we have a oops, I just went to the other page. Let's imagine we have a sequence, like a function f of x, which is defined such that f of x equals 1 for every x which is less than 0, but it equals 5 for every x which is greater than or equal to 0. So if I change color over here, we have a function like this which always equals 1 for x is less than 0, and then it's now defined as 0, and here it jumps up to 5, and it always equals 5 from now on. Well, if we have this kind of function, and now let's say we have a sequence an which equals negative 1 over n. So, this sequence as n goes to infinity is going to approach 0. So, we can just draw our sequence here. It's going to approach 0, so it's going to get closer and closer and closer and closer to 0. Well, now, what happens if we look at the limit as n goes to infinity of f of an? Well, f of an will always equal 1. See, for this value, f of an, it's always going to equal 1. Even as an gets infinitely close to 0, it will never actually reach 0. It only reaches to 0 at infinity, but that's not a real number. So f of an is always going to equal to 1, so the limit will also be equal to 1. But now if we actually look at the function f, at the value of the limit, if we actually look at f of 0, we see that f of 0 equals 5. So the limit is n goes to infinity of f of an, which goes to 0, equals 1, but f at 0 equals 5. So these two are not the same. So we can see that the transference principle only works for continuous functions. But now, how do we actually prove that? Well, the proof is a good exercise because we're going to need continuity. We're going to need the definition of a limit of a sequence and the definition of the continuity of a function. So basically, what we're trying to say, if we want to show this, if we want to show that the limit as n goes to infinity of f of n equals f of x0, well, if we imagine that f of n is just a new sequence which equals to bn, so this f of n is a sequence, an is a sequence, and f of n is just a new sequence bn. Well, how do you show that? How do you show that a sequence has a limit, that it converges to something? Well, anyone that's taken an introductory real analysis course knows that there's a definition basically saying for every epsilon greater than 0, there exists an n from the natural numbers such that for every n greater than that n, we have that f of an minus f of x0 is less than epsilon. And we can imagine, this can be bn minus b, which is the limit of bn. So, this is f of n is just, we can imagine it as a sequence of bn, But this is the classic definition. And we have to show that this holds. We have to show that there really exists an n from the natural numbers such that for every n greater than n, we're going to have that this sequence bn, or, this sequence f of n, is gonna get infinitely close to x0. So how do we actually show that? How do we show that such an n exists, that f of n will get infinitely close to x0? Well, we're gonna need to use we're gonna need to use the fact that f is continuous at x0. And now we can draw this nice little diagram. So we can imagine that this is the domain of f, and then we can imagine this over here is the range of f. And now we can imagine we have our little point here, x0, and let's choose a belt over, let's choose a little like interval like around x0. So here we have x0 plus delta, here we have x0 minus delta, and now we know that the value f takes x0 into f of x0. So we can say that f of x0 is over here. So we know that a function f is going to take a value from the domain into the range. So a function takes any value from the domain somewhere into the range. We know that it takes x0 into f of x0, but since f is continuous at x0, then we know that for any epsilon range around x0, so if you pick f of x0 plus epsilon, f of x0 minus epsilon, we know that even if we pick this range very small, we know that there exists a delta such that for any x, which is delta close to x0. So for any x in this interval, x0 plus delta, x0 minus delta, we know that f will take any x in this interval and it's going to put it somewhere inside this interval. So even if this interval here, even if we choose this interval very small, we know that there still exists an interval on the domain such that, you know, f will take every function from this interval into this interval. And we can see that, you know, in our previous example, why it's not possible here. Well, we can choose, you know, this is our value f of x0, you know, just 0. We can choose a value, like an epsilon value, so f of x0 plus epsilon, this is f of x0 minus epsilon, this is f of x0 minus epsilon. So, you know, we have a little interval here, but now we can choose a delta interval such that f of x0 minus f of any x0 will be in this interval, because whatever delta we choose, you know, which is greater than 0, well, we know that, you know, this is f of x and this is any f of x that's here. The difference here is going to be outside of the interval, so, you know, it's not possible to say this for continuous function for discontinuous functions. But if we actually write this down, how do we actually express this mathematically? Well, we can say that for every epsilon greater than 0, there exists a delta greater than 0, such that for every x which is in the domain of our function f, and such that x0 minus x is less than delta. So for any x that's, you know, infinitely close to this to the point where f is continuous, then we can say that f of x0 minus f of x, the absolute value of that is less than epsilon. So, you know, for any epsilon we choose, there exists a delta in the domain such that for any x which is, you know, delta close to this value x0, we know that f of x0 minus f of x is less than epsilon. And that's exactly what we want. F of x0 minus f of x is less than epsilon. That's exactly what we want over here. We want to show that this is the case, but, you know, in our original definition, we want to show that there exists an n such that for every n, such that at a certain point in our an sequence, you know, if we have a sequence an, like, which converges to the value x0, after a certain point in the sequence, for example, you know, this is our sequence, converges to x0, after a certain cutoff, every point, every an here, well, we want to say that f of an satisfies this over here. So we want to know that there exists an n, that is the case, and we just show that if f is continuous at x0, then for every x which is in this range, so which is in the range x0, so for every x that's basically in the range in the interval x0 minus delta, x0 plus delta, every x in this range, we see that this holds. So we just, now all we have to show is that our sequence after a certain point is always going to be in this range over here. But, well, first of all, we know that our sequence converges to the value x0. So if we imagine our sequence over here in the domain, if we just, you know, let's write our sequence in green, you know, so our sequence is going to have values and it's going to converge to the point x0. So we know that no part of our sequence can mean x0 plus delta. That's a fact, because, you know, it converges to the value x0 and it can never be bigger than that. And we also know that, you know, since the sequence converges, since the sequence has a limit, we know that we can say that since x0 is the limit as n goes to infinity of an, well, then we can say that for every, you know, with our classic definition, for every epsilon greater than 0 there exists an n, you know, we can say that. But now, since, you know, for every epsilon is greater than 0, we can choose a delta. We can say for delta greater than 0, there exists an n from the natural numbers. There exists an n from the natural numbers, such that for every n greater than n, we're gonna have an minus x0 is less than delta. You know, usually the proof goes for every epsilon greater than 0, there exists this, so this is less than epsilon. But since we can choose for every epsilon greater than 0, we can choose that our epsilon equals delta. We can choose that our epsilon equals the value delta, which we have chosen here in this definition. And basically, we know that this is the case because because our sequence converges at x0, we know that there exists an n from the natural numbers, such that for every n greater than that n, an will be infinitely close to x0. So the infinitely many an terms are going to be in this range over here. And that's exactly what we wanted to show. So since we know that like this n that we found over here is precisely the n we were looking for at our definition. Basically, we showed that there exists an n such that for every n greater than that n, our sequence an will be infinitely close, will be delta close to our value x0, and because f is continuous at x0, we know that that for every x in this domain, we know that f of x minus f of x0 will be less than epsilon. So we know that for every x here, it's going to take it somewhere here. So using these two definitions, we just showed that this definition holds. We know that we indeed can find an n, which we found over there, such that for every n greater than n, f of n minus f of x0 is less than epsilon. It kind of, it's a really simple proof, but you kind of really need to see that. To prove this statement, you need this statement over here, and then to show that our sequence really will have all values in this area after a certain n, you need to use the fact that the sequence converges to this value. So it's kind of, you need to use some previous definitions, you need to have some previous knowledge, but basically that's how we prove the statement. That's how you prove the transference principle. And yeah, it's a very important principle in real analysis. It makes sense. We can see in the example that why it doesn't hold if the function isn't continuous. And yeah, that is it. Thank you for watching.